Hi, everybody. This is Mr. Folly again, and welcome to 2.2. We are in the midst of calorimetry, which will teach us how to do the math and explain heating curves and all the stuff that goes with that. So let's hop right into that. All right. So heating curves are going to be our guide to calculations. If a line has a non-zero slope, that means it goes like this or it goes like this. Temperature is changing. Okay, so notice right here, my y-axis is temperature and my x-axis is time. So I'm going to be heating things for a certain amount of time. If the line is flat, the phase is changing. If the line is flat, the phase is changing. If a line has a non-zero slope, temperature is changing. There. These can be combined. So what that means is I could start right here and end here. Okay, so I would have a slanty part and a flat part. If I had solid butter and I melted it and I put it on a doorknob as an April Fool's Day joke, what part of the graph would be shown? The part that would be shown was, so if I melted it, so I have solid butter and I'd melt it, and I put it on there, so then I would warm it up because this would be the temperature of the room. Okay, so that would be from B to C.5. Yeah, halfway between C and D. I made that up. It'll work. My cold Diet Coke warmed up. What part of the graph would that be? Okay, so let's try a different color. Let's go green because Diet Coke is good. So if I started out as cold Diet Coke and I ended up as warm Diet Coke, notice how this whole part right here is a liquid, and that's what my Diet Coke is all the time. So aspartame, kill the bad brain cells for me, not the good ones. So this out of the way. Warming something up. How much energy does it take to heat it up? So if you think about this, how much energy? Well, energy is the symbol Q. Why it's Q is a weird thing. It's a quantity of heat. And the unit for Q, the unit for heat, is calories. How much of it do you have? So I'm trying to figure out how much energy does it take to heat it up? Well, I care about the energy, and I care about the mass. Symbol for mass is M, and its unit is G. What it is determines its heatability. Okay, so we're not making a thermos this year, but we usually make thermoses. So don't be surprised if we do have to make a thermos. Specific heat, the symbol is C, and its units are calories per gram degrees Celsius. So this is its heatability. If it has a large value for C, it's an insulator. Insulator heats slowly. Or really, it takes a lot of energy to heat it up. And an important thing for you to know, triangle means change in, or just change. And capital T, of course, is temperature. Okay. And then, so when I look at this, the energy, how much of it, its heatability, and how hot do you want to make it, that's your change in temperature, right? And that's going to be in degrees Celsius. It could be in kelvins, it just won't be, okay? So that means this equation is the heat equals the amount of heat it takes equals the mass, how much of it there is, its individual heatability, and how hot do you want to make it. So that's one of the equations you need to have in your soul. What is the final temperature if 20 grams of solid copper at 5 absorbs 200 calories of heat? Okay, so I got solid copper, so Q, equation, substitute, solve. Q equals MC delta T because I'm only staying in the land of solid copper. So, what will be the final temperature if 20 grams of solid copper at 5 degrees, 20 grams is mass, at 5 degrees Celsius, that's temperature, but not delta T, absorbs 200 calories of heat. Calories is heat. So my Q is going to be 200. The mass is going to be 20. Now, the specific heat of solid copper, on the end of the notes here, we have a table of everything. Dun, dun, dun. Here's copper. And we're looking for solid copper. Solid copper, 0.090. That's the specific heat of copper. You're going to use that sheet a lot, 0.09. And we're going to solve for delta T, even though we know we're starting at 5. Okay? So when we do this, we're multiplying these times delta T, so we'll do the inverse operation of dividing it. Oh no, oh no. Sorry about that. My oh no was my calculator had dead batteries. But 200 divided by 20 divided by 0.09 equals delta T, which is 111 degrees Celsius. Now that's how much it changed, okay? It's going to absorb the heat, so it's going to go up. So that means this thing is just going to go warm and go this way, okay? So if I started at 5 and I add 111, so the final temperature, T sub F minus T sub I equals delta T, just so you know. But if I start at 5 and I go up 111, it's 116 degrees Celsius is T sub F. What will be the final temperature if 20 grams of solid copper at 10 releases 200 calories of heat? Pretty much the same thing, right? I don't know why I changed temperature to 10 instead of just 5, but again, Q equals MC delta T. Still looking at solid copper. I'm releasing 200 calories. This means the temperature is going to go down, right? The mass is still 20. Still at solid copper, which is 0.09. I'm going to solve my delta T. That is the same exact calculation, which would be 111 degrees Celsius, but it's going to go down this time. So 5 minus 111 is negative 106. Boom, boom, boom. All right. Next one, what mass of liquid mercury can be heated 15 degrees Celsius when 175 calories of heat are added? Hey, that sounds like Q equals MC delta T to me. What mass? So I'm looking for M of liquid mercury. Liquid mercury. I'm going to have to look at my table. Can be heated 15 degrees. I put 2 delta T's in there. That's 15 degrees Celsius. When 175 calories, that's Q. 175 equals M. I need liquid mercury. Whee! Specific heat of liquid mercury is 0.034. My delta T, it's heated 15 degrees, so that's just a 15 there. So to get rid of these guys, I do the inverse operation, so I'm going to divide. So 175 divided by 0.034 divided by 15 is going to be 343 masses in grams. All right. When we tested our thermos, okay, we didn't do that yet, but we're going to. When we tested our thermos, 1,000 grams of water at 20 degrees Celsius was heated to 100 degrees Celsius. How much heat did that take? Notice it's still liquid on both sides. Q equals MC delta T. The mass is 1,000 grams. Specific heat of water. Water. Liquid. 1. And we changed it from 100 to 20 is 80. I don't even need a calculator for that one. 80, 1, 2, 3, 80,000 calories. All right, so that's just changing temperature. We don't have change of state yet. So phase changes, solid to liquid, liquid to gas, the boiling, the condensing, all that stuff. Q equals M delta H. Okay, delta H is the energy to change the state of matter. Delta H fusion is the energy to melt or freeze. Delta H vap is the energy to boil or condense. This stands for vapor. Boiling has gases. Vapors are gases. Vape. M is mass in grams, and Q is heat in calories. There is no C. People tend to call this, I call this M delta H, and the other one's Mc delta T. There's no C in M delta H. So let's take a look. So we have, breathing in 2 grams of benzene will cause brain damage to your dog. Oh, how many grams of benzene will boil at 80 degrees Celsius if 150 calories of energy are added? Will this give your dog brain damage? Oh. Okay, so how many grams of liquid benzene? So we're just boiling this. So Q equals M delta H. Boiling has gases. Vapes are gases. Vaping gases. So how many grams of liquid benzene will boil? So how many grams of liquid benzene will boil at 80? Okay, so let me show you something nifty about this. So I'm looking at benzene. Benzene is right here. Benzene. Now it's going to boil at 80. Notice that means it's already there, okay? So boiling is delta H vaporization, so it's going to be 94. So let's jump up to here. Boop, 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 boop. Maybe I jumped too far. So I forgot already. 94, I hope is what it was. And then it said how much of it? Q was 150. Oops. So let's solve for M. To get rid of the 94, I divide by 94. So 150 divided by 94 is 1.60. 1.60 grams will turn into a gas, so you will not give your dog brain damage. My dog's right here. Hi, dog. So that's it. Your ice cream cake has a heat of fusion of 1.16 calories per gram. If the room provides 500 calories to your cake, how many grams of your 2,500 gram cake will melt? Q equals M delta H. We're melting. Fusion. Okay, fusion is like liquid fusing to be a solid. 500 calories. Q is in calories. That's the heat. How many grams of your 2,500 gram cake will melt? How many grams of your 2,500? That means I want to solve for M. Even though it says the cake's 2,500, not all 2,500 will melt probably. And my heat of fusion is 1.16. So I'm going to solve for M. And 500 divided by 1.16 is 431 grams will melt. Oh. There you go. All right. Combo calculations. Okay, so I'm going to do this kind of together. How much energy does it take to convert 5 grams of carbon tetrachloride at minus 30 to a gas at 85? Notice carbon tetrachloride at minus 30 to a gas. So I think I'm going to be changing temperature. So let's do this. I'm going to kind of do this. Oh, I forgot what it was I'm looking at already. It is carbon tetrachloride at minus 30 to 85. Carbon tetrachloride. So I'm going to look at carbon tetrachloride. And carbon tetrachloride is my old friend right here. This is what I'm looking at. And I'm starting at minus 30, okay? But I should take a note that carbon tetrachloride freezes at minus 24 and boils at 77. So what I'm going to do is I'm going to make a heating curve on these combo calculations. Minus 34 is where it melts, melting point, and the boiling point is at 77, okay? Now this one says we start at minus 30, so I don't care that much about the scale, but here's minus 30, and I'm going to start right here, and I'm going to end at 85, which is above 77, and I'm going to put that over here on this side. Now, when we did the graphs before, remember when you're changing temperature, boop, you go on a slant. But I have to boil. I have to boil my carbon tetrachloride and go flat there. But if I go flat at 77, I'll never reach 85. So once it's all boiled, I have to go right here. Okay? So this means this slanted part right here is going to be, this is all going to be Q equals. This is going to be MC delta T. This is a liquid because it's in between melting and boiling. This part right here is going to be M delta H. It's at the boiling point, so vapors. And over here, I'm going to have MC delta T, but the delta T for this one's going to be a gas. So it's a little bit different for a liquid and a gas. Okay? So overall, I'm going to have Q equals, starting from the bottom and working my way through it, MC delta T, liquid, plus M delta H, vapor, plus MC delta T, this is my gas, okay? So let's look at the question again. How much energy does it take to convert 5 grams of carbon tetrachloride? So I want to point out that 5 grams of carbon tetrachloride, I'm using a different color, 5 grams of carbon tetrachloride is going to be the mass for all of it because the mass doesn't change, okay? At minus 30 would be a liquid, to a gas at 85. So that means I have to heat it up and then I have to boil it, and then I have to heat it up some more. So I'm going to go ahead and do these calculations right here. So the mass is 5. The specific heat of liquid carbon tetrachloride, I think I highlighted it quite nicely. The specific heat of liquid carbon tetrachloride is 0.20. The change in temperature is from minus 30 to 70. Now be careful. A lot of people see this and they see 47. It's not. 30 degrees to get to 0 and then another 77. So it's 77 minus negative 30. 77 minus negative 30, which is 107. Plus, I still have 5 grams. I need the heat of vaporization because I'm boiling my carbon tetrachloride. Carbon tetrachloride's heat of vaporization is 46. And then I got to heat it up some more. The mass is still 5. That's not changing. Specific heat of the gas is a little bit different. Gas is 0.1. And my change in temperature now is from 77 to 85. That's 8. I'm going to throw that in my calculator and get an answer. 5 times 0.2 times 107, enter. Plus quantity. What? Oh, yeah. 5 times, oh, shoot, that's hard to read. Is that 46? I hope. Enter. Plus quantity. 5 times 0.1 times 8, close quantity. I got 341. There you go. So just to show you what I did here, label your start and end points. So notice how that was, I'll get a big ugly marker here. Big ugly gray marker. Start and end points. Boom, 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 boom. Right? So label your boiling point and melting point. Okay? Draw your slanted line up until you reach a melting point or boiling point. And then flatten it out and go. Okay. Each line segment is part of the equation. And remember, slant is mc delta T. Plateaus are m delta H. Fusion and vaporization. So remember, vaporization is the top one, and fusion is the bottom one. And then do math. All right. Specific heat concepts. Let's get back to a pen that's not enormous. Fine chisel, I think sounds good. Low specific heat, that's C. Remember, specific heat is C. Low specific heat changes easily. Low specific heat is called a conductor. It conducts heat and changes temperature quickly. Given equal amounts of energy, a low specific heat will change temperature more than a high specific heat. That's what a conductor is. A high specific heat, so notice how these all go together. High specific heat takes more energy to change temperature. That's why it's called an insulator, right? High specific heat substances are called insulators. If you preheat your oven to 450, okay, so if you put your hand in a preheated oven at 450 and put it in the air, it feels warm. If you touch the metal preheated at 450, it burns, which has a lower C. The metal does because it transfers that heat to you better. Air transfers it poorly, so it doesn't burn you. Metals transfer it quickly, so it burns you. Metals have low specific heats. Water has a high specific heat, okay? Living things have a high specific heat because they have so much water in them. And the other thing you should know is air has a high specific heat. Styrofoam is a good insulator because it has a lot of air inside. Heat of vaporization and heat of fusion concepts. Vaporization is always larger than fusion by a lot. That's because the change from solid to liquid is noticeable. Solid, boom, 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 I'm vibrating, whooshy, whooshy, whooshy. But if I'm going into a gas, boom, whooshy, 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 boom, whooshy, whooshy, whooshy. That is so different that change is incredible whenever you hit that gas part. Okay. So going from solid to liquid, you're breaking bonds, but reforming some liquid. But if you're going from a liquid to gas, the distance increases a ton. This is how you find energy. Q1, Q2, these are charges, right? Charges, I misspelled charges. Charges. R is radius, which is really distance. Which makes sense. If things are farther away, the attraction's less, right? So when this is liquid is boiling, you're breaking bonds, and then they're leaving so much. So imagine if your brother's going to college, but he'll come back, and it's so nice. Oh, we should say Henry's sister. It's so nice, and you'll see him again someday. Versus your uncle is going on the Mars thing, and will be back in 30 years. Well, you know what? 30 years. You're not going to remember your uncle, and that bond will be almost zero by the time you're done. And that is it. Little heat things down there. Some things don't have numbers, like boiling. Rock doesn't boil. It breaks down and turns into something else. And rock has stronger intermolecular forces than water because it has a higher melting point, 950 compared to 0, okay? And a higher heat of fusion, 150 calories per gram versus 80 calories per gram. So rock has stronger forces than water. So on that happy rocking out session, we'll say, I'm sorry, it's 21 minutes long, and toodles.